testing quantum foundations using light, and I request our colleague of ISAR Kolkata, Dr. Nirmalya Ghosh, to chair this session. Nirmalya.
Thank you, Professor Banerjee. And good afternoon, everyone. I welcome you back to this post-lunch session on the third day of our conference on foundation of quantum mechanics. And of course, this session is devoted towards proving foundation of quantum mechanics using light. And we have two very renowned speakers here who use non-classical light to probe fundamental issues of quantum mechanics and foundational problems of quantum mechanics. Professor Rozema from University of Vienna and Professor Urbasi from Raman Research Institute, Bengaluru. At the onset, I must however say that historically, single photons or light has always been used to probe fundamental issues of quantum mechanics or to test quantum theory. And it has been famously said that the double-slit interference experiment actually captures most of the mysteries of quantum mechanics, right? And this is what we have been also discussing in many talks in the last 2 days. But that said, in the last 2 decades, there has been tremendous growth in photonic technologies and in quantum photonics and quantum optics, so that this has opened up new avenues to explore foundational aspect of quantum mechanics, and particularly, for example, to probe quantum paradoxes using non-classical light, like entangled photons generated using spontaneous parametric down conversion, non-classical light like squeeze state of light, and of course weak measurements. And the idea of this session is to look into these recent developments, and our two speakers who are experts in this field and who has made seminal contribution to this area on using non-classical light to probe quantum theories. So they will enlighten us with their own results and also giving us overview of the recent developments. Without much more ado, let me quickly introduce our first speaker, Rozema, Dr. Rozema from University of Vienna. And he is interested, of course, in weak measurements. We'll see that. And also on research interests include quantum state tomography and indefinite causal orders in quantum mechanics, which is an interesting area that you will see. And I'll just briefly talk about his background. He did his PhD at University of Toronto with Steinberg, and then he moved on for a postdoctoral fellowship using Natural Science and Engineering Research Council of Canada's fund to University of Vienna. And he then went on to win a Templeton Independent Research Fellowship, which he continued working there. And now he is a senior scientist there at University of Vienna. And he has made seminal contributions, as I said, to studies on weak measurements to probe Heisenberg uncertainty principles. And also, as I said, that his group was one of the first to actually show the experimental demonstration of indefinite causal order in quantum mechanics. And he will be talking about, I think, both these aspects. So we'll be looking forward to an exciting session after his talk, of course, through his talk and after his talk through the discussion. So without any further delay, I hand it over to you, Lee.
Okay, thank you. Thank you very much for the introduction. Thank you. And I'd also like to thank the organizers for the opportunity to present this work here. It's been a really stimulating conference so far, and I'm happy I get the chance to also contribute in that respect. So the title of this session is Probing Foundational Aspects of Quantum Mechanics Using Light, which is a fairly broad topic, which kind of gives me the opportunity to talk about whatever I want. But before I get this, before I get to what I want to specifically talk about, why are we using photons to study light? Since the first demonstrations of entanglement in Bell's theory, we've really seen an explosion in the number of experiments, demonstrating various aspects of quantum mechanics. And one of the reasons is that photons are kind of a relatively easy platform to get into experimentally. When we take a photonic state, a state of light, and we encode some quantum information in that state, it more or less stays put. It doesn't interact with the environment. So we can encode some qubit state or some higher dimensional state, and it maintains its coherence. We can then also distribute that quantum information over very long distances, and we've seen this in the first session with the experimental violations of Bell's inequality, and then of course also these recent experiments from China where they also demonstrated quantum key distributions using satellite sources. And finally, we can control the states of light very well also. So especially at the single photon level, we can implement extremely high fidelity single photon gates or single photon operations, which overall gives us a very flexible platform. So we can kind of reconfigure our experiments relatively easily to kind of jump on whatever topic we think might be interesting. So with that being said, there are many different aspects of this topic we could focus on. The first one that comes to mind is, of course, Bell test experiments, which we've already talked about quite extensively. So I won't be talking about that. Instead, I'll be talking about different things. There are a few different review articles on quantum foundations, experimental quantum foundations recently. This is one recent one. And I just kind of pulled out the foundational aspects that they discuss in their paper. So they talked about Sorkin interference experiments, which we'll hear about quite a bit in the next talk, I think. Measurements of tunneling time, weak measurements of different effects, and so on. But this is really just a subset of things that have been done. There's, I just kind of thought for a few minutes, and there's also, these induced coherence measurements, weak measurements for a variety of other applications, Hongo-Mandel interference and multiphoton interference effects, which I think is a very interesting platform, which I won't really talk about today, but there's a lot that can be said, and you can also investigate a lot of different physics when you go to multiphoton states. Then there's experiments like quantum eraser, Weidmann-Baum scenarios, and then counterfactual communication, just to name a few. So with all of that, I obviously can't cover all of these topics, so I decided to focus on kind of two main topics. One relatively new topic, that being indefinite causal orders, which I'll introduce in the next slide. And the other is weak measurements. So this is something I worked on quite a bit during my PhD, but I haven't done so much on it recently. But throughout this talk, I'll kind of introduce weak measurements, kind of show you what they're about, and then I'll present one particular example, which is how we can use weak measurements to kind of measure some interesting physics. So in particular, I'll talk about a measurement that was carried out in Toronto on measuring the trajectories of photons as they travel through a double-slit interferometer. Okay, so let's just jump in. So we'll start with this idea of superimposing the order of events. So I'm going to focus on the experimental ideas and what we can do in the lab. But before I do that, I want to motivate this with a very simple game, which was proposed by Oreshkov, Costa, and Bruckner, I guess about 12 years now. And the reason I like to start with this game is it kind of wakes people up. It's kind of a very counterintuitive result, and I think it's relatively easy to understand. So the basic idea is we have two parties, Alice and Bob, and they're going to work together to try to win the following game. So Alice and Bob are each going to flip a coin, and at the same time they flip their coin, they have to guess the output of their neighbor's coin flip. And then after they've both done their coin flip, a referee is going to randomly ask either Alice or Bob to guess the output of the other neighbor's coin. And just kind of thinking logically, there's only a few scenarios that can happen. So we can kind of work through, and as I said, they're working together. So there's kind of two essential scenarios. We can have Alice acting before Bob, or Alice acting after Bob. So let's just consider the first case where Alice acts first. So now Alice is going to flip her coin and get some result. But Bob hasn't flipped his coin yet. So there's no way that she can know the outcome of Bob's coin flip. So the best she can do is just randomly guess the outcome of his coin flip. So in this case, Alice is only going to be able to randomly guess, so she won't be able to, win the game deterministically. However, since Bob is acting after Alice and the two parties are working together, when Bob flips his coin, he can just wait for Alice to tell him the result of her coin flip, and then he can flip her coin and then perfectly guess the outcome or perfectly report the outcome of her coin flip. So now Bob can win this game perfectly. So then overall, if we, then the referee after this is going to ask either Alice or Bob to guess the output. So overall, the success probability of this game is 75%. And this is fairly intuitive, I think. And of course, the other scenario is when Bob acts before Alice, but this would behave the same. So if that was the full story, then there wouldn't be much more to say. But what Oreshkov, Costa, and Bruckner showed in this paper was that there exists a set of processes which can actually violate or can win this game with a higher success probability than 75%. So this, of course, it seems extremely counterintuitive. And in such situations, it's really impossible to say which of the two parties acted first. So by some definition of physicality, in this paper, OCB showed that there are a set of process matrices which you can use to violate this game. However, we still don't know if these processes can be made in the lab, and there are still people who are kind of actively searching for different types of process matrices which we could make in the lab, which can also win this game. However, in the process of this, this led to the idea of what people now call causal non-separability. So causal non-separability, it's similar to entanglement. We define it in terms of kind of what it's not. So first we define what a causally separable process is. And a causally separable process is simply a process where Alice acts before Bob, or Bob acts before Alice, or we can kind of flip a coin and randomly have one of those two processes. So a causally separable process is written here. And processes which can win this game are then causally non-separable. However, as I said, we can't implement this OCB process in the lab. But we can implement a different process in the lab, and that process is called the quantum switch, which I'll introduce now. So another way of thinking about these processes is in terms of quantum circuits. In a quantum circuit, so quantum circuits are a model of quantum computation, which is incredibly successful, of course. But it's not given to us by the laws of quantum mechanics. It's more of a tool that we've developed. It's more of a tool that we've developed. And already in the quantum circuit model, if I just take two gates, U1 and U2, I can already write down something which can't be implemented with a quantum circuit. So if we have gates U1 and U2, and I require you to use each gate once and only once, the only two quantum circuits you can make are kind of sending the qubit first to U1 and then to U2, or the other way around. Of course, this is quantum mechanics, so we can then think, well, what happens if we simply put those two quantum wires in a superposition, and now we have both of these processes, both of these kind of quantum circuits acting in superposition. And this scenario can't be described by a quantum circuit. Of course, you can simulate its evolution by using more calls of the gate, but if you're limited to using each gate only once, you can't simulate the output of this process. So the process that we've been studying in the lab is something called the quantum switch, which is just a slight extension of this idea. We take this scenario of these two superposed circuits, and we add a control qubit. So now, simply dependent on the state of the control qubit, we apply the gates to the target qubit in one order or the other. And the reason this process is interesting is that it's causally non-separable. So it's somehow a weaker notion of these causally these processes which can violate these causal inequalities, this game I presented on one of my first slides. But we know how to make it in the lab. And I want to reiterate that these processes, although they're causally non-separable, they can't violate these causal inequalities. So why might we want to do this, in addition to its foundational implications? So there are a variety of applications, things you can do with these sorts of processes that can't be done with a standard quantum circuit. For example, we can imagine the following scenario, so another game where we take gates U1 and U2, and I give you a copy of U1 and I give you a copy of U2, and I only let you use each gate once. And I give you the guarantee that those gates either commute or anti-commute. And your goal is to tell me which of those two statements is true, with the limitation that each gate is used once. And with a quantum circuit, this isn't possible to do deterministically. However, if we use this quantum switch, We can just go through the algebra. It's relatively simple. After the quantum switch, we end up with this state here where we have the anti-commutator of the two gates in this branch of the superposition and the commutator in that branch. So now if we simply measure the control qubit and we find it to be in the plus state, we know that this term must have been 0, which then tells us that the gates must have commuted, whereas if the control qubit is in the state minus, we know that the gates must have anti-commuted. So based on these kinds of ideas, there have been really a plethora of applications that have been proposed. This is actually a relatively incomplete list of applications. I think I stopped compiling them in 2022, and even then, I don't think I covered everything. So there's lots of other things you can do with this, where the idea is to find scenarios where quantum circuits can't mimic the output of your given application. So this is nice on paper, but how do we build these processes in the lab? So there have been a couple different ways of doing this in the lab. What I'll show you here is one of the first, or the first experiment, which was done in Vienna in 2015. And it was a single photon experiment where we take a single photon, and we now imagine that the system qubit, or the target qubit, is encoded in the polarization state of that photon. It then travels to a beam splitter, and that beam splitter now puts a photon in a superposition of this path and that path, which we can think of as the control qubit. So now, based on the path of that photon, it's going to first go to U1, and then loop around to U2, or it's going to go the other way around. And then after the experiment, we can perform some measurements, which allow us to verify this setup. So immediately after some of these experiments, there were criticisms of loopholes or criticism of these experiments. For example, one thing, the first thing I often hear when I talk about these things is that in our experiment, we have two paths traversing each gate, which means that, because we have two paths passing the gate, doesn't that mean we have two gate uses? There are ways you can kind of argue around this. Through the experiment, only one photon is crossing the gate. So if you were to imagine some hypothetical quantum non-demolition measurement, you would find that only that the photon only passes through one of these paths. So there is really only one gate use. However, it is equivalent to kind of an unfolded interferometer as drawn here. Another point to be made is that you can think of, if you think about this in terms of events, there are actually 4 distinct space-time events, where at time t0, the photon is going through gate U1 and U2, and at time t1, it's going through again gate U1 or U2, but in the opposite order. So this refers to 4 distinct space-time events. And furthermore, these sorts of experiments are not scalable. So a lot of these applications that are being proposed require us to implement the N switch. So rather than acting on 2 gates, we want to use N gates and put them in a superposition of all of their orders. So this would require us to create an interferometer with n factorial path degrees of freedom, which is clearly something that's not scalable. There has been one experiment to date using 4 gates, but they were kind of limited in the number of different causal orders they superposed. And there have been different proposals using different degrees of freedom which attempt to get around these criticisms, but they more or less all suffer the same criticism. For example, one thing you can imagine doing is, if we care about the spatial degree of freedom through the gate, we can try to use a different degree of freedom to control the photon's path. For example, we can imagine the situation where we have our 2 gates, U1 and U2, and now we have these routers. These are just 2x2 optical switches, and we have a time bin qubit coming in. So a photon in a superposition of being in this time mode or that time mode. And now if we simply kind of choreograph the state of these routers, we can do it in such a way that we send the first time bin down to U2, then we flip the state of the routers, which then, instead of exchanging the paths, it's going to transmit the paths straight through. So now the second time bin will go up to U1, and this will put the first time bin down into this loop so that it's now traveling in the opposite direction back towards this first router. We then flip the state of the routers again, and if we keep doing this, you can follow it through, and you can see that we've now implemented this superposition of orders. And we've actually done this experiment, and it works. And it looks like we've maybe addressed this problem. We only have one path traversing each of these gates. However, we still have 2 time bins going through the gates. So if you think about scaling this up to the n switch, we kind of have the same problem, where now instead of having one spatial, or instead of needing n factorial spatial modes traversing each gate, we now need n factorial time bins crossing the gate. There is a proposal that shows precisely how you can implement this, but it's not scalable again. So it doesn't really solve any of these problems. As I said, we still need a resource which scales with n factorial. So, and the main intuition, the main way you can think about getting around this is the problem with these experiments is that they're using a single particle. This same idea with quantum computing. You can imagine trying to do quantum computing with a single photon and manipulating its path degrees of freedom. 4 paths are equivalent to a 2-qubit state. However, we know that this isn't a scalable approach, and essentially that's the same issue with these experiments. So the idea is, instead of using an internal degree of freedom to control the state of the photon, we want to use an external system. So if instead of a kind of classical router, we use a quantum router that we can now put in a superposition state, so we can put it in the state where the 2 modes are transmitted, this kind of bar state, or the state where we cross the 2 modes, the cross state. Then after a photon comes in, it's going to be entangled with the state of the router. So if it exits, it'll exit in this mode when the router is in the bar state, or in this mode when it's in the cross state. And this can be done. There's actually experiments showing exactly this effect using atomic systems, where dependent on the state of some atom in this case, the photon is either transmitted or reflected, and it's done so in a way which generates entanglement between the photon and the matter system. So now if we just take the same geometry I showed you for the time bins, and we replace those classical routers with quantum routers, and we put them in the superposition state, actually an entangled state, where we have the state bar cross plus cross bar, then when the photon passes through this, in the case where the control qubits or the routers are in the bar cross state, we'll follow these black lines where the photon will go first to A, loop around to B, and then exit the experiment, or it will take the cross mode and experience the gates in the opposite order. So now this actually does address many of the criticisms of these experiments. We have only one optical mode per router. Moreover, we can show that we can use these sorts of schemes to implement the n switch with a resource that now scales logarithmically with with n. As a side note, we also can do this. We don't necessarily need these 2 routers. We can also do it with a single quantum router. So it is something that is actually experimentally feasible. So this goes towards addressing these loopholes. So this is a relatively new idea that we haven't actually published yet. So we haven't fully addressed all of these loopholes, but it's pretty clear that it addresses the multiple use and the scalability issues. It doesn't seem to immediately address the multiple events issues, but if you can imagine putting your photon in a superposition of many spatial modes, essentially using a very long photon, in that case, there will be, you won't necessarily be able, well, there's some ambiguity on how you define an event when your system is in a superposition of states. And the question is, can we use these sorts of experiments to kind of address these issues and do a device-independent, perhaps, verification that we really have an indefinite causal order? So just some final remarks on these quantum switches and indefinite causal order. There are, in spite of these criticisms, there are still kind of 2 camps on the experiments that we've done. Not just us, but there's many other experiments. And there are some people who like the experiment, and they still claim that we can think about the experimental implementations of having a definite causal order, and there are others who claim that there are some sort of simulations. And now the question is, should we consider these criticisms as some sort of loophole in the experimental demonstration, or is it something more serious? And then, are there really any of these applications which are interesting enough that it's worth building the quantum switch so we can do something in a way that's more efficient than with a standard quantum circuit? And just a final thought, these processes which violate causal inequalities, we don't know how to implement them. But they kind of exhibit a stronger form of this causal non-separability. The quantum switch itself is causally non-separable, but can't violate a causal inequality. So it's possible that this is some sort of These causal inequalities are some sort of processes which would be kind of akin to a PR box in a Bell scenario, where we can have signaling correlations, where these causal inequality processes kind of have signaling backwards in time. So it's perhaps plausible to think that we might not be able to implement them, but there's a weaker form of causal non-separability which we think we can implement in the lab. Okay, so with that, I'm going to kind of switch gears and move on to weak measurements. So weak measurements were something that were proposed back in the 80s by Aronov, Elbert, and Weidman with a provocatively titled paper, How the Result of a Measurement of the Component of the Spin of a Spin 1/2 Particle Can Turn Out to be 100. What I'd like to do now is kind of explain this paper and kind of show you how you can get this result. But before doing that, I need to introduce this concept of von Neumann measurements, where we imagine that we have some quantum system and we want to perform a measurement on it, but we don't want to measure that quantum system directly. Instead, what we're going to do is take a probe system, some auxiliary or ancilla system, let it interact with that system qubit in a way that the observable we're interested in measuring on the system qubit becomes entangled with the probe, and now measurements of that probe qubit will give us information about this system qubit. If you prefer quantum circuits, we can think about this in terms of quantum circuits, where we simply have a 2-qubit circuit where we have some quantum state which we would like to measure. Say we want to measure it in the Z basis. We can use a controlled NOT gate and an ancilla qubit such that they interact with the C NOT gate, which then entangles the two systems. And now if we perform a measurement on the probe qubit, we'll find that it collapses to state 0 with probability alpha squared, and to state 1 with probability beta squared. So if we just measure the probe qubit in the Z basis, and we construct its expectation value using these experimentally measured probabilities, P0 and P1, we can get the expectation value of Z on the system qubit without measuring it directly. This is, of course, nothing fancy. This was proposed a very long time ago as a model for quantum measurements. This, of course, collapses a system just like you would expect in a standard projective measurement. Because we have this entanglement, when we measure that probe qubit, we're either going to collapse the system qubit to state 0 or state 1. So the state of the system will be decohered, will be decohered as we would expect from a standard measurement. Right, and of course, we can also measure other observables just by putting unitaries around the control qubit so that we can measure kind of anything we want on that control degree of freedom. So now that we have this idea of measuring using a second system, what happens if we just make this interaction weak? So if we make this interaction weak such that the initial state of the pointer is very broad, then when that interaction couples the system and probe qubit, the probe qubit doesn't move very much with respect to its initial width. In language of the quantum circuits, if we imagine that this probe qubit is in the state plus, then after that interaction, we end up with a product state. So now the system is undisturbed, but we don't get any information. So although this doesn't give us any information, we can instead make the state of the probe qubit close to the plus state, but not exactly the plus state. In this state, we will generate some entanglement, and we can read out some information. And if you go through the same math, you can show that simply measuring this control qubit gives us the expectation value of Z of the system qubit as we want. However, we do this without, I didn't put this factor in, we do this without collapsing the state completely. The purity of this system qubit will be reduced by this factor here, which we can think of as the strength of the measurement. And although we don't get information on a single shot, we can now perform this measurement many times. We can perform the measurement many times so that we can build up statistics and read out the measurement that we would like. And this now allows us to do some more interesting things. Because we don't collapse the state of the system qubit, we can perform measurements on it to get more information. So this on its own isn't the result from the Weidman paper. To get the result of the Weidman paper, we need to introduce one additional concept, which is that of weak values. So to get the weak value, what we do is we add essentially conditional measurements. So we do our weak measurement like normal, but now we also measure the pointer system. And we imagine preparing the system in some qubit and then measuring the system qubit in the state F after that interaction. And we can now ask questions like, in those instances where the system started in state I and ended in state F, what was the value of this observable in between? And if we just go through the same math, so this is using some particular states which were proposed in this paper. So we start with the system qubit in a superposition of the plus and minus states, and we post-select on one of these states F. And you go through the math, and you'll find that now, in this case, this kind of post-selected value, instead of being directly the expectation value, gives us something different. It gives us this kind of tan of alpha over 2. So in this case, as alpha approaches pi, we have this expectation value exploding. So we seem to have what's referred to as weak value amplification, where we have expectation values that can approach infinity, which is weird when you're thinking about measuring a spin particle or some discrete observable. So in general, you can generalize this result for arbitrary unitaries and arbitrary input states, and you have this overlap term. So you have the initial state and final state, and then you have the overlap of the initial and final states in the denominator. So now when this value gets small, when this overlap gets small, this value gets very large. And this leads to this effect called weak value amplification, which you can now imagine using to perform more precise measurements. And this was initially demonstrated by Paul Kwiat's group in 2008, where they used this effect to measure the spin Hall effect of light. There are many other subsequent demonstrations of this amplification effect. And most of these, there are many other demonstrations of this, but it comes at a cost. Because we're doing this post-selection, we're now throwing out a lot of our data. So it turns out you don't necessarily gain too much in terms of signal to noise, so you have to find the right scenario where you have some, say, systematic drift in your measurement results, and then you can really see advantages from this weak value amplification. I just want to mention one value from my former group, Ephraim Steinberg's group, where when they published the paper in Nature Physics, it came out with the title Weak Value Amplification of the Nonlinear Effect of a Single Photon. But the original paper that Ephraim wanted to publish with was how the result of counting one photon can turn out to be the value of 8, really intending to show this original Weidmann result. Right. So in addition to this amplification idea, you can use weak measurements to probe other kind of foundational aspects of quantum mechanics. So now I'd like to give you an example which doesn't use amplification, but instead allows us to study other effects. So this is based on a proposal by Howard Wiseman back in 2007, where he showed how you could use weak measurements to measure the trajectories of a photon as it travels through a double-slit interferometer. And the trajectories we measure, I just want to mention, are completely equivalent to the Bohmian trajectories, or at least mathematically equivalent to the Bohmian trajectories originally proposed by Professor Ghosh in 2001. So the reason that this Wiseman result is interesting is because he doesn't necessarily make any assumptions about what we want to measure. So throughout the paper, he refers to this character, the naive experimentalist, which we take the place of, and claims that if you give a naive experimentalist access to an interferometer, he would essentially come up with this idea of weak measurement. And he finds it, and then draws the conclusion that these trajectories, which you kind of would imagine are kind of the most natural thing you would measure if you tried to measure the trajectories of a quantum particle, are equivalent to the Bohmian trajectories. So what does this look like? So we imagine we have some double-slit interference pattern, and now we want to measure the trajectories of the photon as they travel that interferometer, and they're interfering. So what we need to do is measure the position and momentum of the photons at every point in space. And using standard projective measurements, we of course can't do this reliably, because measuring the position or measuring the momentum will disturb the other variable, so the trajectories that we would reconstruct wouldn't necessarily make sense. And we want to do this in kind of multiple planes and see what happens, and kind of stitch together the trajectories. So since quantum mechanics, since strong measurements don't let us do this, we can imagine what would happen if instead of using projective measurements, we use our weak measurements. So to weakly measure the photons, we're going to use the following scenario. So now instead of thinking about qubits, we're going to think about the system as the spatial profile of the photon. And we're interested in the two variables, the position and the momentum of those photons. So in the experiment, we're going to take a second degree of freedom of that photon, the polarization degree of freedom, and use that as the probe system. So we have two systems, but now they're encoded in the same particle. And now the idea is we want to couple the momentum, the transverse momentum of that photon, to the polarization state. We can do that experimentally using a birefringent crystal. So this birefringent crystal will impart a phase on the photon dependent to the momentum. So roughly speaking, the longer the path the photon takes through the crystal, the larger the birefringence it sees. So we couple this momentum to the photon. And now we're simply going to perform the right measurement on the polarization state, on the probe state, and learn about phi. And we're going to do that post-selecting on the position. So at every position, we're going to do this measurement. And what Howard showed in this paper was that when we do this, what we're essentially doing is measuring the weak value of momentum, where we prepare the system in some initial state, and some initial transverse profile, and we post-select on it the photon being at every point x in the interferometer. So I'm not going to go through the details, but this is the experimental apparatus which was built in Toronto. And when you reconstruct these trajectories, this is what you get. So you see that at early propagation distances, you have trajectories leaving from these two areas, which is where the two slits are in the experiment. And as they travel to the far field, the trajectories bunch in distinct locations, and they kind of avoid other locations. So these areas where we have a lot of trajectories arriving correspond to the bright fringes of an interferometer, because a lot of trajectories end there, so we find a lot of photons there. Whereas these points where we have no trajectories or very few trajectories are the dark spots of our interference pattern. So now we've actually reconstructed the trajectories of the photon in the presence of interference, so without collapsing the state. So if you look at these trajectories, the other interesting feature about these trajectories is that the trajectories never cross. So this means if you have a photon in the upper slit of that interferometer, it's always going to end up in kind of the upper half plane of the interference pattern, and the same for the lower slit. So this seems weird, kind of counterintuitive, because if we block one of these slits, then we'll see the photons from this slit. We'll just see the diffraction pattern of that photon through the slit, and this in general is going to have some probability to find the photon anywhere on that interference plane in the far field. And if we try to formalize this a little bit more, we can try to imagine doing a witch path measurement or a witch slit measurement. So say we perform some measurement up here where we measure which slit the photon goes through. Of course, doing this is going to introduce witch path information, which is going to destroy the interference. So that's why in these trajectories here, we don't see interference. But we can do this. We can imagine doing this measurement where we measure the slit, where we measure the slit of the photon. And now there are cases, you can show relatively easily that there are cases where we find the photon in this slit, but in the far field, the photon ends up in the lower half plane. So that's represented by this black line, which then crosses this boundary between the slits. So the quantum trajectory that you could imagine would be that, well, now the photon went from here to here, so we can just connect those points by a line. But that would correspond to this trajectory, which if we trace back, originates at the lower slit, which is then in contradiction with the value of the which way measurement. So this was pointed out back in 1992, and these trajectories were called surrealistic Bohmian trajectories, which was used as argument that Bohmian mechanics is inconsistent with what we actually observe. So now the question is, can we address this question experimentally? Okay, well, first a bit of Bohmian intuition on this. So what the Bohmians would say is that Bohmian mechanics is inherently non-local. So if we measure the state of that which way particle at the beginning of the slit, we're measuring at one time, but the photon continues propagating through the interferometer. And as that photon's propagating through that interferometer, the state of that which path measurement actually should evolve in time. So now we want to try to see what that actually looks like in the lab. So the way we can do that, first thing we need to do is actually somehow implement a which path measurement. So we did this experimentally by entangling two photons. So we just created a polarization entangled state, which is fairly straightforward to do. And then we took one of those photons and we sent it to a polarizing beam splitter. So we put it in a superposition of two paths and then set the polarization to be the same. So now, in general, we have the entangled state where this upper photon is in the state H. If this upper photon is in the state H, we know that the lower photon is in this upper path, and if it's in state V, then that photon is in the lower path. So now we can use the same technique to simply measure the trajectories in this experiment. Of course, doing so is going to destroy the interference. So the first thing we see is maybe that's evidence that our which path measurement works, because we've introduced this which way information, so now we have no interference in the far field. But we can bring the interference back. So this isn't necessarily a Bohmian result. But if you think about kind of the quantum eraser, if we perform a measurement on this upper photon, we can say measure that photon in the diagonal basis. So when we measure that photon in the diagonal basis, what we're doing is actually collapsing the lower photon into a given state. So for example, just going through a little bit of algebra here, you can show that if you find this upper photon in the diagonal state, so a superposition of H plus V, then we collapse that lower photon into the state upper plus lower. So it's in a superposition of the two slits. Whereas if we find it in the state antidiagonal, so H minus V, then we have the superposition with an opposite phase. So doing this brings the interference back. And I think this is a nice result. It's nothing necessarily new. It's just in a different system. This is, like I said, the quantum eraser. But now to verify this Bohmian prediction, we want to do essentially this effect, but in reverse. So what we're going to do is focus on a single trajectory, and instead of post-selecting on the which way photon, we're going to post-select on the interferometer photon. So this is an example of what happens for one of these trajectories. So what we're doing here is we're sending this photon through the double slit, and we're looking only at cases where we find this slit photon at points along this specific trajectory. In those cases, we look at the state of the which way photon. And now you can see what happens. So the color here is correlated to the color on the Bloch sphere. So at early times, when we measure the which way photon, we find these red points here. So all of the results are kind of clustered around the bottom of the Bloch sphere, telling us that the photon went through the lower slit. However, if we, instead of post-selecting at early times, we start post-selecting on later times, the state of the which path photon, the state of the which way measurement photon actually evolves up to the Bloch sphere. In the limit, when we go to the far field and we find our photon in between the slits, we find that the which path photon is actually in the diagonal state. So it's in a superposition of upper plus lower. So this shows essentially the Bohmian mechanics argument, where we see that the particle state, the state of this photon depends on the slit photon. So now these arguments of surreal trajectories from the Bohmian point of view are kind of countered by saying that we haven't considered the evolution, and the state and the which path photon is only reliable when we kind of measure it at the right time. I do want to point out, though, that we've done this with weak measurements. So although this is maybe consistent with the Bohmian story, this does not provide evidence for Bohmian mechanics. In all of our measurements, we've had to average. Because we're doing weak measurements, we can't read any information out on a single shot. Instead, what we need to do is repeat our measurement many times, which requires averaging. And that means we can't follow a single photon, and we can't make correlations between the which path photon and the split photon. So we can draw these conclusions only on average. Right, so these trajectories are mathematically equivalent to Bohmian mechanics. And as I said, we can't, although they're equivalent, and maybe you find this as some support for Bohmian mechanics, it doesn't provide any proof for this interpretation because we're doing this on average. And if you tried to do this really on a single photon, a single shot level, you would of course collapse the state of the photon and you would get completely different trajectories which wouldn't agree with Bohmian mechanics. Okay, so to conclude my talk, I hope I've shown you that photonics allows us to address many different aspects of quantum theory. I've shown you kind of two examples, some of our experiments on indefinite causal order, where I introduced this idea of an indefinite causal order more generally, and then I've shown what can be implemented in the lab, pointed out some of the loopholes and criticisms, and I've also pointed a way where we might be able to close some of these loopholes in the lab. With respect to weak measurements, I introduced weak measurements, showing you that it's simply a well-defined measurement procedure. There's nothing magic about it. It requires post-selecting on your data, which can lead to surprising results. Using this post-selection in some contexts allows you to achieve very large weak values, which people have tried to use for amplification to perform more precise measurements. But there's more things you can do with weak measurements, and I focus on this one example where we used weak measurements to measure the Bohmian trajectories. So with that, I'd like to thank you for listening. The causal order, I didn't really present any specific examples of our causal order work. Most of that work was carried out in Vienna, but there's groups all over the world doing these things. The trajectory experiments were done in Toronto. I was involved in only in the surreal trajectory experiment, but I wasn't working on the first experiment. But I hope you found them interesting. So thank you for your attention.
Thanks, Lee, for a really illuminating lecture on both weak measurements and on proving indefinite causal trajectories using photonics. And I'm sure that we'll have a lot of questions, interesting questions later on. So we'll move on now with our next presentation, which is to be given by Professor Urbasi. So let me quickly introduce her. As I said, that both of our speakers have done some seminal experiments on proving foundational quantum mechanics using light. So we'll also hear from Urbasi, and I particularly remember one experiment. I think she will be talking about that famous triple slit experiment that many of you must have heard on validating Bond's rule. Right. Yeah. So let me quickly introduce her. Professor Sinha is now the head of Quantum Information and Quantum Computing Lab at Raman Research Institute. She did her PhD in Physics and Material Science from Cambridge University and followed with a postdoc at Cavendish Laboratories at University of Cambridge, and then further postdoctoral research at Institute for Quantum Computing, Waterloo. And then she joined, of course, Raman Research Institute. She has, of course, received many honors and awards. I will not mention all of those, but I just point out a few of those. She has recently been awarded the Rashtriya Vigyan Puraskar Yuva Shanti Sarup Bhatnagar Award in 2024 for physics, of course. And she was also appointed an Emmy Noether Fellow in 2022 at Perimeter Institute, Canada. And she is also a fellow, Homi Fellow, of course. And with this brief introduction, I will hand it over to Urbasi.
Can you hear me at the back? Yeah. So thank you very much to the organizers for this opportunity. It has been a fantastic conference so far, and I hope Lee and I don't disappoint you with our session. Lee was, of course, fantastic. Now let's see what happens with mine. So it is wonderful to be able to contribute to this conference. And of course, thanks Nirmalya for that kind introduction. Probing foundations of quantum mechanics using light. So this is the topic, and so I continue with the same topic. I found this very nice article, which says experiments with light at the single photon level have historically been at the forefront of fundamental tests of quantum theory, and current developments in photonic technologies that enable the exploration of new directions. So when we were first told to talk on this, we both wondered, how we are going to cover this, because it's a whole conference by itself. And then we did the thing of saying that we would choose some themes and cover only those themes so that at least we can do some justification to those themes. So my theme is what tests can we do to test the quantumness of a single photon? Okay. So now when we talk about the quantumness of a single photon, the first thing that comes to mind is photon anti-bunching. This is probably historically the most, the first test that people did to figure out the singleness of a single photon. Okay. And so what do we mean by that? So look at this first figure here. You have a single photon. It's an indivisible entity. So this is my source. Okay. It is incident on a beam splitter. And so it will either get transmitted or it will get reflected. It won't do both because it's an indivisible entity. So both the detectors do not click simultaneously, and hence at zero delay between these photons, there is, between these signals, there is no correlation. Okay? So the correlation would increase as we increase the delay, and this is what is called this famous G2 measurement, right? And so G2 at tau equal to 0 being 0 is the first sort of, proof of the singleness of a single photon. Okay? So far so good. This is the first chapter of a quantum optics textbook. So I will go chapter-wise. I'll go to the second chapter of the textbook, which will increase the complexity a little bit, and also basically give you the flavor for my talk here, which would be about how quantumness of a single photon manifests itself in different scenarios, and what are the ramifications and what are the surprises it throws in these various scenarios. So that would be how I would pitch this. Okay? So photon bunching, this is the second theme, or not theme, sub-theme. So what is photon bunching? So this is essentially what happens when you have two indistinguishable photons, which are incident. So the same figure, now look at this one, these are two indistinguishable photons, which are incident on two ports of this beam splitter. Okay? And so what would happen is, if there is no distinguishability factor, then both of these photons would either choose to exit from one port or the other port. They won't exit from one and the other, right? So that is the basic idea of this bunching. And so if there is a distinguishability factor, say a slight delay, then there is a chance that one of them would get reflected, transmitted. So the correlation would be again a 0 at 0 delay in arrival time of the photon, but will increase as the delay is increased. Again, a 0 measurement. Okay? But this time, you have two photons which have come out. Nothing has come out this side, or vice versa. So again, 2 times 0 is also 0. And so in this context, so this is what it is. This is for the students, if you like math and so on. So this is how mathematically it comes. But because of lack of time, I won't really go through a lot of the math. You can, of course, find it in textbooks. And so this is the general idea. Two photons incident on two ports. So if there's a single photon, then of course it will do either. But if there are two photons, what happens was the question we are asking. And this is the math which tells you that they would exit either one way or the other, forming what is called the 2, 0, minus 0, 2 state, which is in fact the first level of what is a known state, right? N-O-O-N, where n is equal to 2. This is the first such state, and you can have higher order states and so on. So this is what gives rise to what is famously called the Hong-O-Mandel dip, because this dip was first measured here. So there are two seminal papers actually, which I would refer to for this particular photon bunching experiment. This is, of course, the one by Hong, O, and Mandel. But this experiment, the focus was different. Here it was more about this distinguishability factor that I told you about. It was not so much about the quantumness of the single photon. It was, how distinguishable and how indistinguishable you can make things. And one of the things which can make things distinguishable is if there is a little bit of imprecision in the time measurement. So if this time measurement, of course, there will be some small, 0 is never 0. So what is that 0 will determine that distinguishability. And so they were able to succeed in measuring sub-picosecond time intervals between two photons, and by that implication, and this is what they call the fourth order interference technique. So their concentration was on telling you, this precision they were able to achieve, which gives you an almost 0 here. It's not quite 0, this is theory, this is experiment, but this is a very nice dip. Okay? So this was the focus. But this was preceded by this paper, where, so this has Rupamanjari Ghosh on this, who incidentally, of course, has an Indian connection. She was the Vice Chancellor of Shiv Nadar University in Delhi NCR, and this, of course, was done during her PhD days. I won't tell you, you can almost imagine that this was some time ago. Okay, but this was a very seminal contribution where they did the entire theory of how this would pan out for 2 photons in parametric down conversion, which has been introduced several times before this, right? But the experiment that followed was even more interesting, where they showed the observation of non-classical effects in the interference of 2 photons. In fact, this is the paper where they talk about the quantumness for the first time, whereas the HOM paper was more about that distinguishability factor and the precision. Okay, and so, in fact, if you see their paper, they say that, if these fields, I won't worry about which equations they are, but there are fields, and they assume that the sources are randomly phased. Then they go on to show that this dotted curve that you see, the coincidence versus separation, this dotted curve has a limit of 50% visibility for a classical light, and for quantum, it goes higher. And of course, this was a first measurement, so it's not a very high visibility, but clearly much, much more than the 50%, right? And so this was the quantumness result, okay? So one thing that I said, which maybe you recall, is that they did not worry about the phase between the input pulses. So what would happen if you worry about the phase? So this is again not just them, so this is a whole bunch of very important results with O's PhD thesis as well, right? Where they have said that as long as the visibility of the coincidence dip is greater than 50%, no semi-classical field theory can account for the observed interference. So 50% is the limit of classical, beyond 50 things are quantum. This was what was known, and with various people reporting that, okay? So what happens if you include the phase is the question. So this is actually the, this important formula here, which is the second order correlation of classical fields. You can see that, this is the first, the intensity correlation function, right? But what is important here is this term here, or any of these terms, you can see that it depends not only on the time delay tau between the input pulses, but also on the probability distribution of the relative phase. So as we said, they ignored that earlier. So now, if you have no control over the phase, the formula predicts a 50% dip in correlation, and this is what you will end up simulating on Mathematica or whatever you like, okay? But now you see that the visibility depends on the probability distribution of the relative phase. So if it's a uniform random phase over the interval 0 to 2 pi, this will come out to 0.5. I'm sure you can do this in your head. The students, I'm sure, and also the non-students can do this in their head. No. I'm sure Professor Banerjee is doing it in his head as I speak, because, but then having said that, so this becomes 0.5, okay? But now, if the phase is chosen from the set 0 to pi, not 0 to pi, 0 and pi, okay, with equal probability, which is, of course, this, then the visibility is 1. So the correlation shows a 100% dip. And of course, also remember that this washes out the first order interference. That is also important, that what you're going to see is, in fact, now whether it is second or fourth is a matter of choice. So if you think in amplitudes, it's fourth order. If you think in intensity, it's second order. So it's a matter of what you like to call it. And so this is a bit more of the detail, but you can find all this in this paper here. So this is important, that you can actually have classical pulses and perfect phase control between them and show a 100% Hongomandel-like dip, okay? And so this is something which was obviously missed because phase was not even considered in these various experiments I showed. And so this is the experiment that was done, where, of course, the classical pulses were generated painstakingly, actually using an electrical experiment. So you have signal generators, arbitrary waveform generators, so on and so forth. And this is the result. So when you have no phase control, it's just random. You get this, close to 50% dip. But when you choose that between 0 and pi, as I mentioned, then you get an almost 100% dip. And this is using classical light, okay? And of course, the experiment also contained the photonic version, which is using SPDC photons, where you naturally get also a close to 100%. No surprises there. So classical pulses can be used to mimic a 100% Hongomandel dip. Hongomandel effect is thus not a true signature of quantum. So especially when it is used as a diagnostic of photon sources, it's a very common usage that, you measure this dip and figure out whether your source is classical or quantum, but with classical, we have just showed you a 100% dip. So what next? And that is, of course, is the world is not going to end. We have a resolution. And so the resolution is that, here we, of course, have the beam splitter and we measure the Hongomandel dip. But now I can continue with this as an input state to an interferometer. a Mach-Zehnder interferometer, and see interference. So now if I have a truly quantum source, then an interferometer will give you an interference. But if that source is just masquerading as quantum, because this was done in a way that these classical pulses have this phase control and that is how you measure it, is that still going to retain that quantum behavior? That's the question. Will we see interference? And so, of course, in order to answer that, again, this was done classically using the electrical version. And so now, what we would, of course, usually do is measure interference and see what happens. But experimentalists in this audience will know that if you measure it with a Mach-Zehnder, you'll have to do phase stabilization of the Mach-Zehnder, and you bring in lots of complications which is not necessary in this. So one thing is for you to see, if this is a Mach-Zehnder interferometer, which it is, and the intensity is I here and I here, then this will just be I square, what you would measure. But now if I put a, some sort of a blocker in one of the arms, then in the classical case, this would just be I square by 2. So you'll just miss one of the contributions, it will be I square by 2. So if you measure this, you will get a point, and this is what we got actually in the experiment, which is as close to 0.5 as you would expect. But now in the quantum case, if you again put this blocker, we actually have a superposition state to begin with, right? The 2, 0 minus 0, 2 state. So this blocker is going to collapse the superposition state to either 2, 0 or 0, 2. And which, of course, is this, right? So 2, 0 goes to, has all these contributions. So instead of just one factor of half, you will introduce another factor of half as well, which will give you a quarter. So this is a trick. So instead of measuring interference, getting a bad visibility, and working very hard to improve it, you just distinguish between these ratios, whether you get a half or a quarter, and of course we got a very beautiful quarter as well. Okay? So which tells you that when we had a photonic input, when we had a HOM shown with photons and that acted as an input to the interferometer, we saw interference, whereas when we had this other state we generated, which was using the phase control, it showed that HOM-like dip, but it failed to show interference. Okay, so we can obtain this 100% visibility with classical pulses with proper phase control, and this is what we got experimentally. But then this is possible from classical pulses, but what is the true signature of quantum? So this was a novel 2-photon complementarity experiment done with both single photon and classical. While classical pulses fail to demonstrate wave-particle duality without change in the source setting, the photons exhibit both particle-like and wave-like behavior in the respective settings. So this was an interesting, result which tells you, which makes you question about, the tests for quantum, because HOM is the second chapter of a quantum optics book, but you have to handle it with care, because you can apparently get these 100% dips even without photons. But of course, somewhere down the line, photons win because you see interference. Now, moving on to another facet of complementarity, this time using weak measurements, and thanks to Lee, this part becomes very simple for me because he did such a fantastic job of describing weak measurements, so I can only show you the little result which is related to this particular topic without again explaining weak measurements. Of course, we talked and ensured that certain things were introduced, him being the first speaker. And so this was an interesting facet, and this is another result from, again, Aharonov and his collaborators, where he proposed the quantum Cheshire cat, and he referred to it on his first slide as well. Now, what is a quantum Cheshire cat? Now, what is a Cheshire cat? Now, I don't know if there is anyone young enough in this audience to be actually reading fairy tales, but then hopefully you recall that in Alice in Wonderland, there was a cat who was on one branch of a tree, whereas his grin was on the other arm, right? A grin without a cat and a cat without a grin, that is your folklore fairy tale Cheshire cat. But of course, by using weak measurements, by using weak interaction and post-selection, as you nicely introduced, we can actually see this Cheshire cat phenomena in quantum, experiments. Okay, and many experiments have been done to see the quantum Cheshire cat. I'm not going through the whole detail, but in all of them, what they have ended up doing is, in one set of experiments, they have shown the presence of the particle or the weak value of the projection operator of the particle in one arm, and in another set of experiments, they have shown some property in the other arm. Again, a weak value, okay? But they have not shown this simultaneously. Now, of course, that is a criticism, that if you don't show it simultaneously, how do you know it ever belonged to the same particle? It could be something that you're seeing in one run and some other thing contributing to the other. And so this is what we set out to do, in fact, and so this is the idea. And so this is my pre-selected state, and here I have the weak interaction for the projection operator, and I have the weak interaction for a polarization component, okay? And then I see the interference pattern, and by observing the shift in the pointer, I'm able to figure out the weak value, okay? And this is the gory detail of the interferometer, and you know, this experiment took us 4 years, not because we are particularly bad experimentalists, but because, you know, it was a hard experiment. And also, you know, to get everything right and all the interpretations, it was a daunting task, but we managed to do it all right. And so this was, I will skip the details, so you can read, okay? So this is the result. So you can see, so this is, of course, the weak value of the projection operator as a function of the post-selection, okay? But this post-selection 0 is that Cheshire cat point. And so you can see the weak value being 1 for the projection operator. And in the same experiment in the other arm, we see the weak value being 1 for a polarization component, which is the sigma x component of the polarization. And so you can see that, you know, these happen simultaneously. And so this joint measurement is what made this very interesting. And of course, you know, this is another way of representing it where they are peaking around the 1. Okay, and so this is a very interesting, you know, facet where you sort of have a seemingly you know, a position being measured in one arm and a property being measured in the other, but in a weak measurement sense. So weak interaction followed by post-selection is the only way in which you can do that. So in a limited sense, you are sort of seeing a particle-like separation of properties, but through interference. So, you know, it makes you think a little bit of a facet of complementarity, which maybe we did not think of earlier. So this is the third part. Now, going on to the fourth part, which was also you know, talked about by Lee on his first slide as one of the topics which he's not going to cover. So I'm going to cover it, and this is higher order interference in quantum mechanics. Again, of course, light will play a very important role in this story as well. And I would like to quote Raymond Laflamme, who was my postdoc mentor, that a quantum world is a place where there is no penalty for interference. And of course, in games, it will lead to some red card, yellow card, whatever it is, right? So that is what we went on to do. And so interference and some rules, this is Professor Raphael Sorkin. I don't know whether he was writing this seminal paper during this time, but that is usually how serious he mostly is. And a delightful scientist to interact with if you ever have the opportunity. So this was his seminal work in 1994. So he says that, you know, interference describes the deviation from the classical additivity of the probabilities of mutually exclusive events. Okay? Now, if additivity holds, we, as in he, calls it a sum rule. So a sum rule says that an interference term I equal to 0. Now, let's just make this a little bit more intuitive. So if you have a single slit, okay, everything is going through. So it's very trivial. So everything goes through. So IA is PA. P being the probability of measuring something through the single slit A. Now, if you have two slits, then it becomes interesting because, of course, you know, this is the probability when both slits are open, and this is when only one or the other is open. And this difference is non-zero, and that is why we say we have interference, and that is what makes things quantum and so on and so forth. So IAB being non-zero, of course, is consistent with quantum mechanics. Now, what happens when you have three slits is the question. So this is the next level in the hierarchy. So IABC, similarly, is probability when all three slits are open, minus the sum when only two of them are open at a time, plus the singles, okay? And now this is algebra again. I'm sure you're working it out in the head. If you just expand this term and use the fact that you would say that, okay, this is simply psi A plus psi B plus psi C mod whole square, and you just expand, then you will see IABC is 0, okay, from algebra. And this is assuming superposition principle in this sense as well as the Born rule for probabilities. And so this is what Raphael said, that a triple slit experiment can be used as a test for the Born rule for probabilities. Because of course, if we measure a non-zero I3, then that would mean a violation of the Born rule. And you know, and so this was the seminal 1994 paper that he wrote and made this wrote this proposal, and it's a beautiful paper. It has many other things. Why does Born rule need a test is a question. Of course, you would say, I'm using it all the time, and I'm sure there are people who are working on different kinds of experiments where you're using Born rule as an ingredient. But of course, those are indirect tests. For everything, you need a direct test. So that, that is what you're measuring and nothing else. And so the precision test to test something directly has its own, place in history, and that is what he wanted done, okay? And so, and of course, apologies to most of the audience here. It doesn't matter how beautiful your theory is. It doesn't matter how smart you are. If it doesn't agree with the experiment, it is wrong. I did not say it, right? And so that I can just get away with this, but then, as an experimentalist, I have to keep going to the experiments, which, of course, let's say, happened with I3 as well, right? And so this is Max Born, and this is his paper, his work on Born rule. And very interestingly, if you see in his paper, he says phi is the probability. And then as an addition in the footnote, he says mod psi squared. So it's not like he actually said the square in the main text, which is a very interesting historical anecdote, which makes you think, okay, there is some merit to testing Born rule, because even the great Max Born did not really think of his mod psi square to begin with. Of course, it is there in the footnote, so he was all right. So this was, this is the how do you test the second sum rule. So you have the 3 slits, so that will give you PABC if all are open, and if you close them like that, you will get the 2's, and then if you close 2 of them and open only once, you will get the 1, right? And so this is the experimental schematic. So essentially, different kinds of sources were used in this experiment. So this is a laser source. So in fact, I was involved in this experiment, of course. And so a classical laser light was used to see what happens. Then attenuated laser light, which means getting it down to a single photon level, but then also SPDC-based single photon source. So all 3 were used to check what happens to this quantity, which we now call kappa, which is the normalized Sorkin parameter. And this was the paper which was published when we had the nice results after 3 years of frustration. Okay, and so this is how it looks. So this is the mask with these 3 slits with the dimensions, and then we had another mask where we had those combinations, So we would just move it up and down and open up 3, 2, 2, 1, and so on, but in a random order, so that we don't introduce any systematic error. So that was done. Okay, and these are the results. So this is the result for the strong laser, this is the attenuated laser, and this is a single photon source. Of course, you can see that as we go lower and lower in photon number, the errors will increase, because there is this somewhat this rule of thumb of being proportional to 1 by root n, the Poissonian error. So n becomes smaller, right? And so then naturally error bars are bigger. But then the result was that for these 2, we were able to bound kappa to 10 to the minus 3, but for the photon source experiment, it was bounded to 10 to the minus 2. So this was the first result for putting a bound on I3, and this was 10 to the minus 2. Many experiments followed after this. So for instance, this one, in which instead of using slits, they used a 3-path interferometer with shutters, okay? And this was the result. And so you can see that it was also, it improved the result by 1 order of magnitude. It was 10 to the minus 3 now, even for the photon case, okay? This was a 5-path interferometer version, which looks like that, and this was the result. So the quantum case, again, it was 10 to the minus 3. So nothing better happened than 10 to the minus 3. So this has been the bound. It has not only been about photons. Many other systems were also used to measure I3, okay? And so, for instance, we have this matter wave diffraction. Then we have atomic test of higher order interference, okay? Then we have SPDC and matter waves somehow combined. Then we have this strongly driven V-type artificial atom. Here we have this using a nanophotonic chip, okay? And this was Ray Laflamme's experiment using NMR, okay? And this was Marcus Arndt's group, where they used some 500 AMU, I believe, molecule, and were able to do this experiment. For all these experiments, kappa remains 0. And it is 10 to the minus 3 is the best bound that we have seen so far, okay? So this is the situation with measuring the Sorkin parameter. But then comes this realization that, there are other ways to get a non-zero Sorkin parameter. So non-zero Sorkin parameter, of course, original motivation from Raphael was that if you measure a non-zero, that will lead to a violation of, that will mean a violation of the Born rule. But then, if you introduce some kind of interaction, then also you can get a non-zero, and this will be within the realms of quantum mechanics. And so this started a whole new branch of experiments and theory where these things were tried out to measure non-zero, but this is not going to have any ramification of quantum violating Born rule, okay? And so this is, again, my favorite, double slit is coming up again. Nirmalya already told us it's a beautiful experiment. So if you have a double slit, and if you have a single, A open, any source, any detector, let's not worry about it. Let's just say this is a boundary value problem, right? You have two slits, you have a source of something, and then you apply this as a boundary condition. So if you have B closed and A open, solution is psi A. We are still quantum physicists, we'll call it psi, okay? And then if we close A and open B, we'll call it psi B. Now the question is, if I open both of them, is the solution psi A plus psi B? And of course, that is what is used here in plotting these, and famous books have also used this. But then comes the question, is this true? So now recall that the superposition principle is actually applicable when the boundary condition remains the same. If you have many solutions, you can have a linear combination, that's also a solution. But if the boundary condition changes, then it's not so. A open, B open, and AB open is not the same boundary condition. So this is not right. Okay? So there is a correction required. And so this can be seen actually. So this was seen in an electromagnetic wave simulation using finite difference time domain approach by this group, where they showed a non-zero kappa coming out of simulation for electromagnetic waves. Okay? But what about quantum? So the first non-zero estimate of kappa using this boundary value argument was done in this particular work, okay, where it was proposed how to measure a non-zero Sorkin parameter within the realms of quantum mechanics, and to actually put a number, because all these things are fine, but if you can do an experiment and show a non-zero, then it becomes finer in some sense. And so this paper proposed how to do that, okay. And so this is the Feynman path integral approach. So I won't go into the details, I'm sure most of you are very well aware of it, but see, this is a classically dominant path. This is an example of a subdominant path, but all paths are allowed in path integral. So it's a sum total. So these paths are traditionally ignored. And that is why we get that zero. As soon as you bring in a subdominant path, you will get the non-zero, and we called it non-classical path. On hindsight, we shouldn't have. Led to a lot of questions, quantum path, non-classical as in classically subdominant. Okay? And so the green line is that, and so then essentially, observation of a non-zero kappa, which is expected from the proposed modification of the wave function hypothesis, would also serve as an experimental validation of the full scope of the Feynman path integral formalism. This was an offshoot of this as well. So these are the numerical results. So this is just your interference pattern, but the blue curve you see tells you how kappa modulates as a function of detector position. 10 to the minus 5 is the order expected, and the the values for the experimental parameters were taken from this paper. Okay. Likewise, and so kappa is non-zero, and likewise even for electrons from this paper, it is of the order of 10 to the minus 8. This was followed by deriving an analytic form of the non-zero Sorkin parameter. Okay, that was numerical, I showed you. This is analytical, and it is a simple formula. It is a length scale dependent formula. So lambda to the 3 by 2 by d to the half w, lambda is wavelength, d is interslit distance, w is slit width. So you can see that you can come up with an experiment where you can measure kappa, because otherwise you're buried in noise. Okay, and so the beautiful matches with the previous ones and also with FTDT simulations. And all these FTDT simulations take a lot of compute power. Ours ran on the standard laptop using Mathematica. So somewhere, having an analytic hold is nice. And I'm now, it seems like I'm batting for the theorists here. So I have to move to experiments before I become one myself. And so the experiment again. And so this was an experiment from the Boyd group, okay, in Ottawa, where they claimed that they were sort of measuring our theory using photons, okay? And so this was their thing. So this was a triple slit experiment as well. But the interesting thing is that their slits were etched on a plate which was covered in gold. Obviously, they're a rich group to begin with. But then gold actually is a material which leads to a material-induced enhancement for kappa. This was shown in simulation. So they sort of artificially also managed to increase the value by bringing in an interaction which was not geometry dependent alone, but also a material induced enhancement, and this was their result. Okay, and so these are the experimental data points, and the blue line is the theory curve. Now if you are discerning, you will notice that the data points are only at the minima. There is nothing at these peaks or at the slope. And I can actually fit a parabola and call it a fit as well, but I won't do that. But then it's valid suggestion anyone can have. But of course, this was not my experiment. But they could not really do better than this because they didn't have the precision given the length scale of the experiment. They didn't have the precision in the detector to be able to see those intermediate points. So that is where they were. But however, we could do better. And we, of course, decided to go out of the lab. And of course, any opportunity to do that, students are always very happy. But this was not a picnic. This was an observatory 100 kilometers from RRI. So you may remember, what we are doing with this non-zero kappa is telling you that this is a boundary value problem. So if you change, this does not really need photons to show this. You can also show this with electromagnetic waves, because we showed the beautiful match also with photons, electromagnetic waves. So this is what we ended up doing, a radio astronomy inspired experiment. Okay, and this is how it looks, and these were the parameters. So you can see this was in the gigahertz domain. The experiment was very large scale. And so this is what we would measure if there was no non-classical path, obviously a 0, and this was our result. You can see there are data points in the peak, dip, and the slope, as we would like to get, generally, at different distances. We also killed the paths by putting baffles and then brought it back, almost similar to your, bringing back interference. And so kappa becomes 0 as soon as you kill the paths. And so all this was shown. So this was the first observation of non-classical paths. And tunability parameter makes this unambiguous, because that couldn't be done in that gold experiment, which was so small. And Feynman path is equally valid in classical and quantum regimes. So it was never meant to be 0, the Sorkin parameter. There are non-zeroness. So beyond that, you have to measure the non-zero. And so that is the thing. We still don't have that non-zero, the real non-zero, which will give us the violation of Born rule. And simplicity is beautiful. You can do experiments on a field. So these are, so then there are other ways in which people have thought about the non-zeroness. So this is, higher order interference between multiple quantum particles interacting non-linearly. As I said, bring in some kind of interaction and you can get a non-zero. And so this was one approach. Lee was on it, yeah. And so this was the experiment using a non-linear triple slit. Likewise, this group, they actually tested it using multi-particles. So we had a single particle 3 slit. These guys had 2 particles 5 slits. And they said that, they were able to see something. But then again, so these are all attempts to see the non-zero, but this is not that non-zero we have been after. And we are still after that, okay? Now I go back to my, thank God you're awake, yes? So now you will appear in this talk for the next 15 minutes more than once. So you told us yesterday that you were very happy that today you're not giving a talk. Of course, this is Nicolas Gizin, and so he said, oh, today I'm not going to be on the stage, so I had to falsify that, so at least you will be there in my talk, in spirit. Okay, and so this is something which I wanted to put up for a couple of slides, because it came out of a discussion after this beautiful talk that Nicolas gave on the first day about this quantum physics needs complex numbers. And I had said that I'd put up a slide to show you the Perez test results, and, at least the reference so that you can have a look at it. And so that is what I'm doing here. Okay, and so this is a paper in which we tested both the Perez test and the Sorkin test together. Okay, so the Perez test is based on the superposition principle. Okay, and so it tells you that if it's a superposition, then this relative phase comes in, which is what gives you this field. So the gamma parameter comes. So if it is 1, less than 1, or greater than 1, so it will be complex, real, or quaternionic. Okay, and of course Sorkin tests we have just gone through. So we did both these tests, but then of course on a quantum computer as well. So we tested the foundations of quantum mechanics on a quantum computer, and then we assumed we are okay with the foundations and found how noisy these computers are using the foundations as a benchmark for the noise in a quantum computer. And so this was very nice, and of course you should read this to see how beautiful current day quantum computers are, and that is why all of you need to work hard on it to make them even more beautiful than what they are. Okay? And so this is a reference for a Perez test. Likewise, there is this reference as well, where they actually did a test of hypercomplex quantum theories using a metamaterial coming from top down, so they put a bound on the hypercomplex. Okay, and so this is just an addition because of the first day's discussion. And interference is at the heart of quantum. So with that, the final leg of testing quantumness of a single photon. And in this, I will tell you about testing the quantumness of a single photon using the Leggett-Garg inequalities. Again, thanks to being the speaker in the 6th session, this has been introduced and discussed many, many times. So again, I have an advantage here. So I will not introduce it again, but tell you how it was done and the semi-device independent random number generation that we did from this. Okay. So now this brings us to the Nobel Prize in Physics 2022, which of course was also discussed, which was given to these three obviously very, very famous gentlemen for their, and not just them, their groups. I mean, nobody does an experiment alone, more or less, right? And so it's of course a huge effort. Entangled photons, establishing violation of Bell inequalities, and pioneering quantum information science. And Harold gave this beautiful talk, which talked about all the experiments so far and so on. But in case you missed the talk or didn't look it up again, you can have a look at this article that I was invited to write, where I actually read all the experiments and summarized for you. In case you don't have the time to read all the experiments and go through them, sometimes we run out of time. So this may not be a bad resource either. Okay, and so, and also the Nobel Prize website. So again, going back to Nicola, his second appearance, he gave us a beautiful discussion on loophole-free Bell tests as well. And of course, these are the loophole-free Bell tests, which were almost simultaneous that year, and so on. So now, why is a loophole-free test such an important achievement? I think it was already covered on Monday, but then the point is that, loophole-free is important because it tells you, okay, that the underlying theory is fine, and, we all like that. We like things to be good and fine, but it is not just that. It is also that the particles can be, it's demonstrated that they're entangled, but also a particular source of entangled particles is working as intended and hasn't been tampered with. So if there is no loophole in your experiment, Manov as an eavesdropper cannot just come in and use that loophole and kill my security, which he usually does as the last person to ask a question in any discussion session. Okay, so then of course comes this point that this is what gives you these perfectly secure QKD and these DI, RNGs and so on, which were beautifully discussed by so many people before. And also this article, if you wanted to read, summarizes this really well. So loophole-free test is important, but this was for, particles which generally tend to be more than one in number and which are separated from each other, that is non-local, right? So now, of course, there is Tony Leggett and Anupam Garg who came up with the Leggett-Garg inequalities, which, as you know, are temporal equivalent of the Bell inequalities. What happens when it's a single particle that we are talking about? That guy is not going to be there and here. So what are we going to do with it? So we need a time analog, and that is where Leggett-Garg comes in, and our experiment comes in, which is the first loophole-free interferometric test of macrorealism using heralded single photons. Okay, this was, of course, the first violation of the Leggett-Garg inequalities, and it was achieved, published in early 22. Of course, achieved before that. There is a timeline between achievement and publication, and this was indeed a proud moment for our lab because it again took us quite a lot of time to get this done. And now it is being used for secure quantum communications. Okay, so original motivation for LGI was to use it for probing the possible limits of quantum mechanics, as was said many times before. This classical quantum divide and so on, right? And these are all these various molecules and experiments which have been done to test them at larger and larger in masses, okay? But then comes this point. In recent years, the quantum mechanical violation of LGI and its implications have been extensively studied for various tests of microsystems to prove their non-classicality, okay? Single nuclear spins, electrons, and photons. So it becomes a very strong test for quantum. That was the theme, of course, right? And so all this without involving locality. So key features of our experiment is the first loophole-free experiment where both LGI and the Wigner form of LGI inequalities have been decisively violated. It's a comprehensive refutation of classical worldview. Also what we did is, we found out what will be the violation of both the inequalities if we take all the non-idealities of the experiment into account. What would be the new bound? And that is also crucial because it will not remain 1.5. It will lower. And so we actually analyzed that and had the match of that with the experiment. So we definitely matched with quantum predictions, okay? And then non-classicality of single photon states. So now I go to a snapshot from Peter's talk where he did a beautiful job of telling us about various things, and of course so did Hendrik, but then I don't have a snapshot from his talk. So about the testing the macroscopic limits of quantum mechanics, all those beautiful experiments. Here you have to see that experimental observation of superposition with increasing size, mass and complexity is of key importance for testing the validity of quantum mechanics. So you would notice that it is not just mass which is one way of doing this macroscopicity. There are other degrees of freedom which will also define macroscopicity, and this already Peter did a beautiful job, and this is another snapshot of this very nice paper where quantum superposition at the half-meter scale. Okay? So this is an important thing for us to realize. It's not just, you know, mass is increasing. There are other ways of defining macroscopicity which is context dependent. Okay? And so, I mean, you know, the question comes, a single photon, what is macroscopy? After all, a single photon is famously massless and chargeless. But then that's not the point, right? And so here we have, you know, the concatenated Mach-Zehnder geometry and our macroscopicity. So what is macroscopicity? Essentially, you know, how well you are able to distinguish between the two states which are in this macroscopic superposition. What is the, you know, the parameter which defines that? Okay, and for us it is characterized by the ratio of the spatial separation of the two arms of the interferometer to the wavelength of the photon, which is very large. It's of the order of 10 to the 4. Likewise, you know, in the squid experiments where Tony Leggett was involved, we have this, you know, counterclockwise and clockwise flux, and the separation between them. That is their macroscopicity parameter. So this is important to realize. It's not just about mass. It's context dependent. And so in this experiment, we closed and or circumvented all these loopholes: clumsiness loophole, detection efficiency loophole, coincidence, multi-photon emission, and preparation state loophole in the same experiment for the first time. But no experiment can ever be loophole free, right? Some loophole may remain, and then of course comes the challenge of closing that when it comes. But these are the well-known loopholes, and none of them, and no experiment before that had closed it all for the first time. And of course we have used photons. And this is the actual schematic. It is slightly more complicated than the proposal. It involves a Sarniac geometry. And there's a result which is very important, is the experimentally measured value, and this is the quantum mechanically predicted range. You can see that we have a beautiful match. The other thing we did is, you know, in order to satisfy NIM, or the non-invasive measurability, we did what is called satisfaction of the two-time, no signaling in time. Okay? And so this is how well we were able to satisfy that. So that's the detail. Okay, and the final part, again, Nicola, where he again did a beautiful job, was telling us about how Bell inequality violation gives rise to random numbers. Okay? So now what about Leggett-Garg inequality? Does it do the same? And this is a beautiful, news and views written by Pironio himself. He was the author, you know, an author in the first paper which generated random numbers from, you know, a non-locality, right? And so he says, more problematic is the size of the author's random number generator. It is comprised of measurement stations that are 187 meters apart. Because, you know, in order to do a loophole-free experiment, you need to be outside each other's light cone to prevent subluminal signaling between the photon pairs. This distance might be reduced in the future when faster things can happen, right? But it is hard to imagine how it could reach the dimensions of a more standard electronic hardware, because 200 meters is really quite long, right? And so at most a few centimeters using foreseeable technology. And so this is what led us into figuring out what would happen if we use Leggett-Garg instead, because that's a single particle experiment, it can be contained. And so this is, of course, you know, Howard Weizmann and Eric Cavalcanti in this beautiful work. They talk about another beautiful work by Masane Asin and my favorite person by now, Jizan, who has said, you know, in this paper that they have previously noted in their work that, you know, the assumptions of signal locality plus predictability are also sufficient to derive Bell inequalities. So it's not just about the usual realism and locality that I talk about, but it's actually locality and predictability together can also be used to do a similar derivation of Bell. And so these authors, Weizmann and Cavalcanti, actually used this and did the full derivation in this paper, and also showed that, you know, by violation of Bell inequality, or in fact violating predictability, which leads to randomness. So they were the first people to show that you can actually use this two conditions, derive Bell, and show that their violation leads to random number generation. And of course, you know, so for this, after this, you know, setting this as a backdrop, the time equivalent derivation was done by Shiladitya Manik and Shujit, okay, where they derived these inequalities under a different set of assumptions, namely the assumptions of predictability and no signaling in time, which is of course needed for LGI type inequalities. As a novel implication of this derivation, they find application of LGI in randomness certification. So they, you know, did the equivalent derivation for the predictability based derivation and showed that it is possible. Okay. So now this brings us to this paper where we showed single system-based generation of certified randomness using Leggett-Garg inequality. And here, you know, we have theoretically formulated and experimentally demonstrated a secure scheme, okay, for semi-device independent random number generation by using these LGI violations within a loophole-free photonic architecture. Okay. And we have done the quantification, both analytic and numerical, and they are in perfect agreement. Okay. And so essentially these are the salient features. Earlier only certification was shown. We have quantified this generated genuine randomness using both analytical and numerical methods. And we show the security against state preparation, very crucial, and derive the bound on genuine randomness under such conditions. We analyze the effect of, you know, making this NSIT slightly different from 0, which is weakening it and seeing what happens to this generated randomness, and also the memory effect, which was a big part of Pironio's first paper on this as well. And of course, the piezo resistance, we experimentally generate genuine random numbers through the violation of LGI using a loophole-free photonic architecture. And so this is the snapshot of the Bell experiments. You can see the distances here. Okay, and in our case, of course, distance is irrelevant because it's a single particle and time. This is what makes this a very nice first step, and of course, lots to be done in improving various things. These are our assumptions, and that is what makes it semi-device independent. We would like to go towards a scenario where we have one more slide, two more slides on this assumption. Okay, so random bits were generated. So these are the various random bits. I won't go through the details right now, but so we generated around 1 million bits at this rate. But of course, this is the first step. We will do many other steps going forward to make this higher and so on and so forth. Conclusion, so semi-device independent random number generation using temporal correlations doesn't require that large spatial separation and preservation of entanglement over distance. Loophole-free experiment to generate bits is at an appreciable rate. Secure against any attacks on the initial state, and rigorous estimation taking into account possible side information available to the adversary and employing extraction and amplification. These are future steps. I would like to end that, after all this, when it becomes quite heavy, if you're giving the talk, it's not as heavy, but if you're listening, sometimes it's too much detail. There is light at the end of this tunnel, so I'm finishing my talk now. And I would like to finish this with this letter, which I received, which we all received, you know, the whole group at IQC, where I was at that time, from the son of Max Born, after we did that first experiment to test Born rule, okay? And so as I said, you know, these experiments, it's not just about foundations, testing foundations with light. Any research, whether theory or experiment, I would say, can be frustrating when things don't work. And so you need to troubleshoot and derive joy in that. Sometimes you don't do that either. Then you look at these sort of letters, which comes from the son of Max Born himself, okay? Thankfully not from, I mean, it has a Born as a signature, but it's thankfully the right kind of Born, because spooky action at a distance is only so nice, right? And so I thought I would like to tell you of the great surprise and pleasure your paper in the July issue of Science has given me. I'm the son of Max Born, and I'm generally gratified that theoretical work he did in 1926 when I was 5. So he was born in 1921. This letter came in 2010. Another math problem, okay? Should now receive experimental confirmation 3/4 of a century later. He is a biomedical scientist, and he says he didn't really understand his father's work, but they had a very close bond, and he was very, very glad when some physicist friend pointed our work out to him. You know, this is a letter which teaches us humility. Right, you know, son of a great man, and he was a fantastic researcher himself. He passed away a few years ago, but then, you know, and so this is what I look at when things are petty around me. And so with that, thanks to all the current members of the group who I have pictures of, all the previous members of the group who also have pictures of, but it would be a very bad slide, and all these funding agencies without which I would have no pictures or slides, and for your attention.
Thanks, Urbasi, for a really enlightening lecture covering, so this height is not matching with me, covering the basics of quantum optics. It is starting from bunching, anti-bunching, to going to such higher order interference, Leggett-Garg inequality. I am sure that we'll have a lot of questions after the break. So we'll now break for tea, and we'll be back here exactly at 4:30. And of course, yeah, so Dr. Ritesh Singh will be collecting the questions.